Okay, well, yeah, I'm not sure I'm going to have better stories, but I am absolutely delighted to get Joe's attention. Hello, Joe. First of all, congratulations. I mean, really an amazing moment. And it's, I think I met Joe at least, maybe earlier, but 21 years ago. It was in 1993 that I came to the KITP. That was 1 year after Joe had been here. And he felt like a bit like an older brother, maybe to me, at some level. And, older brothers, sometimes, as much as possible. And, and Joe's reputation has preceded him. So I was probably a little intimidated, but that was before I talked to Joe, really, because, once we started talking physics, I realized, of course, Joe's brilliant, but he's fun to talk physics with. And also I realized that Joe can speak many different physics languages, and I found it, I would say, among all the people in particle physics, string theory, Joe is perhaps the easiest for me to communicate with, and that's a real pleasure. And I think it's partly testimony to the fact that Joe can think about problems in many different ways. And I'm trying to think that when I first came out here. Let me see, we were over in that other building, I guess, right? For at least 2 years you were probably there, right? And it was a smaller KITP then, I think. And I got to know some of the string theory postdocs, Amanda and Loris Thralacious. I don't know if he was over here, yeah. And Shamali, do you remember? Yeah, no, okay, sorry, Joe. Okay, I apologize. But yeah, so well, Andy Strommingen was referring to the early 90s as a period when Joe was in a particularly creative state, and that was also the case actually in condensed matter physics. And I've just listed 2 papers that Joe wrote, which are in condensed matter physics. The one I'm particularly fond of is, of course, the one that we wrote together with this fellow Charlie Kane. Charlie was a postdoc, not here at that stage. And this was phenomenology. I mean, we made a prediction about edge states in the nu equals 2/3 fractional Cornwall Hall effect. And there was very nice confirmation in 2010 by Modi Heibelem's group. So congratulations to all 3 of us on that. But in condensed matter physics, well, in any experimental field, really, things are always more complicated than they initially seem. And so I would say the jury's still out on this, because there's been recent reports that upstream moving neutral modes exist even where one wouldn't expect them in some fractions, so like nu equals 2/5. But so that story continues to develop. Now, in recent years, I haven't talked as much physics with Joe, which is a shame in many ways. And I was sort of thinking about why that was, in particular, maybe the last couple of years. Well, I was down at Caltech for a year. That's certainly one reason. But I think there's another reason, and that's this. There's Joe looking at me, I don't know what the firewall is, but it sounds like something you wouldn't want to get through somehow, or any case, maybe Joe can come around it or something, or I'll have to come to the backside, or whatever the front or backside is. So, I'm a complete outsider to string theory, to black holes. I follow at the level of Scientific American and Lenny Susskind's books. I don't know, slightly above Scientific American level. I don't know where Lenny is. So I hear about black holes, obviously the event horizon, does quantum mechanics break down or not? The firewall, is it very hot or is it not hot at all? Is the event horizon thermal or is it not thermal? There's entanglement going on. Things are entangling with other things. I can't really quite fathom what's entangled with what. But among my other confusions really is just trying to understand the equivalences and differences between thermal entropy and entanglement entropy. And so that's something that I've been thinking a little bit about, in collaboration with Tarun Grover, who's a postdoc here at the KITP, and 2 graduate students, UCSB, Jim Garrison and Ryan Mishmash. I'm not really going to tell you the motivation for this work, but I'll tell you what we think we might be finding evidence for, which is possible hidden locality in thermal eigenstates. And I'll tell you what I mean by this. By way of brief introduction, I'll just remind myself of what thermal entanglement entropies are and talk about the eigenstate thermalization hypothesis, which remarkably, in one condensed matter context, is broken down severely, and that's in the context of many-body localization. But many-body localization, as I'll briefly mention, has classical degrees of freedom in the model Hamiltonian. So it's not a fully quantum mechanical model. So it's in some sense kind of, perhaps a cheat, at least with regard to the eigenstate thermalization hypothesis. So what I want to ask is, can the ETH break down in a fully quantum many-body system, a translationally invariant quantum many-body system? And the definitive answer is maybe. And I'd like to describe 2 things. One is a new wave function diagnostic. I mean, we hear about entanglement entropy. The way I view entanglement entropy is you take a wave function, you stick it in, you turn a crank, and out comes a number, and you maybe have to stick in the region that you entangle with other regions, and you look at how that scales. But there's many other ways to try to characterize wave functions of essentially infinite number of degrees of freedom. And so I want to talk about a wave function diagnostic, which is really beyond entanglement entropy, and it's a diagnostic which involves making measurements everywhere, but only partial measurements. So on every site you make a measurement, we want to make a partial measurement, and you induce some locality, and the question is, how much locality can you induce? Can you induce full locality by making local measurements or not? And we propose the possibility that there may be so-called quantum disentangled liquids, which are thermal states in which there is a hidden locality, and you can project onto a local set of degrees of freedom by only making partial measurements. So thermal and entanglement entropies, okay. Thermal entropy, canonical ensemble, system in contact with the heat bath. The thermal entropy is basically just counting number of states. It doesn't care what the eigenstates look like at all. It's kind of amazing, right? And of course, it's extensive at finite temperature. It grows with the volume. Okay, the entanglement entropy, you would have thought, since it's something to do with a single eigenstate, should depend on what that eigenstate looks like. So the entanglement entropy, of course, is you take an eigenstate in this region, you look at a bipartition, you trace out the density matrix, the degrees of freedom in region B, to get the root density matrix, and then you look at the entanglement entropy. And that measures somehow the entanglement of the degrees of freedom in this subsystem A with this larger piece of the system B. But the entanglement entropy is going to depend on the, of course, on the wave function. So it's a little surprising that it's that it can, in some situations, be as simple as the thermodynamic entropy. But let me show you one sort of a condensed matter physicist view of entanglement entropy, which is coming from numerics. If you take a one-dimensional spin chain, like a chain of 16 spin-halves interacting with first and second neighbor interactions, possibly, and you look at what's plotted here is the entanglement entropy when you divided the system into 8 sites and 8 sites. So half the system versus energy. And down here, the ground state has low entanglement. It's actually going to have an area law. And here you can look at the ground state. The entanglement entropy is a function of x, and it's very flat here. That's the area law. And then you have all of these many, exponentially many finite energy density states. And those high energy states have a volume law, entanglement entropy. And so you get this, in a large system, it will just look like a inverted, I guess, a triangle. And that's that's the entanglement entropy going linearly with the size of the system. And it's rather nice that when you look at this, the maximum entropy state, which is consistent with an entropy per unit length, which is log 2, for the spin-half system. And so the maximal entropy state, and entropy in general, has something to do with a lack of information. So if you have maximal entropy, presumably means you have minimum information. And what is the information you have that you don't have? It's the local information. It's information in region A when you don't have access to looking at region B. So I wanted to sort of emphasize my understanding of volume law states, which are really quite remarkable. They're intrinsically non-local. And so let's focus on, in fact, the maximum entropy volume law eigenstate. That eigenstate possesses no local information. And it's like Alice and Bob sharing an EPR singlet, or Joe and I sharing an EPR singlet. You have your spin, I have my spin. We have no local information until one of us measures it, and then we get it. But before we make the measurement, we have no local information. And not possessing any local information is very different than entropy in the classical context. When you first learn about entropy in classical system mechanics, you choose to not have information. I mean, Boltzmann, didn't know that he could have tried to get in there and measure the trajectories of his putative classical particles. But it's a choice, whereas in a quantum system mechanical system, you actually don't, when the entropy is very high, the entanglement rate is very high, you don't have local information, and it just doesn't exist. It's entangled. It's non-local information. It's entangled. Okay, good. So the Eigenstate thermalization hypothesis, Josh Deutsch at UC Santa Cruz and Mark Sverdnicki, among others, were people to start really focusing on this. And this was really trying to look at quantum system mechanics at finite temperature in the canonical ensemble versus the microcanonical ensemble. And the ETH is basically the statement that the microcanonical ensemble for a large system with a given eigenstate at some finite energy density is equivalent insofar as all the correlations you can measure in region A to what you would measure in the canonical ensemble in a system of the same size embedded in the heat bath. And another feature of the eigenstate thermalization hypothesis is that many-body eigenstates with nearly the same energy have identical, basically the same correlation functions inside. They all look the same. Moreover, in the eigenstate thermalization hypothesis, it follows that the thermal and entanglement entropies per unit volume should be equal to one another. But can the eigenstate thermalization hypothesis break down? And I already mentioned that yes, it can, in the context of a remarkable phase called the many-body localized phase, which was first discussed, I don't know, about 10 years ago only, in condensed matter physics. And what we believe, based on work by a lot of different people, is that if you take an isolated, interacting, quantum many-particle system in which those quantum particles are placed in a random potential, and that potential is static and doesn't depend on time, that you can be in a many-body localized phase. And the character of the many-body localized phase is that that you can have all of the eigenstates having an area law entanglement entropy, even the ones at finite energy density. And the thermal entropy, the number of states in this system, still grows exponentially with the volume. So the thermal entropy grows with the volume, but the entanglement entropy of any of the states grows with the area law. So there's a locality that's induced in these many-body localized wave functions by the presence of this random potential, basically. And the physics is quite remarkable. There's a lack of thermalization which is going on in this many-body localized phase. Basically, the particles don't serve as a thermal bath for their nearby particles, and it's because there's really a discrete local spectrum due to the random potential. You can sort of think of particles in a box. And moreover, in this many-body localized phase is conserved quantities. For example, if you have conserved charge or even conserved energy, they do not propagate. So if you take a many-body localized phase and you just add some energy here, it just stays there forever. It doesn't propagate. There's zero thermal conductivity. But actually, what's even more interesting, in a way, is that entanglement does not propagate. So if Alice and Bob were embedded in a many-body localized phase, and Alice yells, waves, does anything she wants locally, there's no information that can be transmitted. There's no way that she can change the entanglement that she started with, perhaps at some initial time, with Bob. So it's really, there's a disconnect, and
these things always go to the lack of transport and the lack of entanglement always come together.
Well, I mean, if you can move anything, you can entangle, basically, right? So if you if you can't entangle, you can't move anything, basically. I mean, I think, yeah. Entanglement's the thing which is hardest to stop moving. It's the hardest to, well, this is the question. I mean, in this many-body localized phase, things don't entangle because they're localized. They can't propagate. Yeah. So in some ways, it's a simple concept, but what's surprising about it is that's true even if the energy density of the state is high. So there's a lot of energy locally, and you can add more energy locally, and that energy just vibrates around and moves back and forth, but it doesn't propagate.
This definition of NBL means that there are no states, finite energy states.
Well, okay, so the simplest cases are when you put the model on a lattice, and maybe you go to one dimension, and then there's a finite bandwidth, and you have very strong disorder. Then you can show that basically, numerically, that all of the many-body eigenstates are area law. It's believed to be the case that you can have situations where the low energy density eigenstates are area law, and then there's a many-body mobility edge, and then the higher energy density states could be volume law. But there's been just some recent numerical evidence that finds that many-body localization transition, a mobility edge, and that's pretty amazing because you change the energy density and you go from a state which doesn't thermalize and is stuck to a state which does thermalize. And Tarun Grover here has been thinking about the nature of that transition, and it's a very interesting kind of transition, which is not, I don't think, very well understood. But,
Is it possible to change this random potential so you can have a crossover between the area and the volume?
well, not really. I mean, okay, this random potential, we want it to be statistically homogeneous. I mean, so over here it looks, on average, the same as it does over there. I mean, so that's what I'm thinking about. So, but if you change the amplitude of the random potential, that's, then if you make it small enough, or if you make the repulsive interaction strong enough, you can get out of the many-body localized phase into a thermalized phase. But the random potential, is a fiction in the sense that the random potential really is treated as a classical frozen set of degrees of freedom. And now we believe everything in the world is quantum mechanical. Now it's of course legitimate in some context if you have a huge separation of timescales. If it's an impurity in a solid and it lives there for 10 days, and the electrons are zipping around at 10 to the minus 14 seconds timescale, well then you can basically treat it that impurity as static. But let's imagine we're not in a solid, and we're in a liquid or a fluid, or in a translationally invariant system, a system in which symmetry has not been broken. And so we can then ask, can ETH break down in a fully quantum mechanical system? Okay, so the quantum mechanical system I want to have in the back of my mind is a gas or liquid of atoms, neutral atoms, isolated in a box, prepared in a many-body eigenstate with energy E. And here I'm thinking that it's an energy per unit volume. Is that I'm allowing myself to vary. It's like varying temperature. Imagine this big green thing is the nucleus of the atom, and there's one electron. This could be spin-aligned hydrogen, possibly. Well, what presumably happens is we vary the energy density of that eigenstate. Equivalently, you can, if the ETH holds, it's like varying the temperature. Well, at low temperatures, depends on, of course, the density, what low temperatures really means, but if it's a sort of physical densities, masses of the hydrogen atom, this would be in the range of, let's say, 10 to 1,000 degrees Kelvin. One would expect to see an atomic liquid. Atoms bounce around, and that's it. Or is it? We'll come back to that. But what if you raise the temperature or look at the energy density to be very high, like 10 electron volts or higher? Then, surely the electrons are going to ionize off the atoms, and you're going to have an ionized plasma. Okay, so the question I want to ask is, are the eigenstates of the low energy density eigenstates that describe this atomic liquid qualitatively the same as the high energy eigenstates which describe this ionized plasma? And the canonical answer to this question, I believe, at least people have asked about it, and I've thought about this for about 30 years. I've always thought that a neutral gas at low temperatures and a plasma at very high temperatures are in the same phase. There's no phase transition that goes between them. There's no change in symmetry. Well, we now know that things are more subtle, possibly, because you can have to maybe think about the entanglement. So, but the reasons, I think the canonical answer would be that everything's the same, atomic liquid's the same as the ionized plasma, that surely the eigenstates will both have volume law entanglement. There'll be a finite energy density. One might say, okay, also that the atoms, even if the atomic liquid is at low temperature, there'll be some ionization. There'll be few atoms which lose their electrons, even at low temperature. And the presumption always has been, in my head at least, is that you'll have a low density of ionized electrons at low temperature, and those thermalize independently. You have this background of how do we know that's true? This background density of electrons is banging into the ions, and it's not. In fact, what do we even mean by when we say the system is ionized? And maybe that's part of the problem. I mean, an ionized plasma and an unionized atomic liquid, it's not clear how you could define the difference, and that's part of the issue. And how can you, but on the other hand, how could you characterize the thermalization of these ionized electrons? We have an intuition about that, so one might want to, to think can one try to characterize that ionization at the very least. Okay, so what I want to very briefly describe is this new wave function diagnostic, which tells one something about ionization, and then propose a set of these new finite temperature multi-component fluid phases, quantum disentangled liquids. So the wave function diagnostic is the following. You take a volume law wave function, let's say for this atomic system, capital R are the nuclei coordinates, little r are the electron coordinates. And you do two things. First, you measure the positions of the nuclei. And then there they are. And they're frozen. And you hold them. And then you project the wave function onto the state with the nuclei in the positions where you just found them. And then you define an electron wave function for the unmeasured electron degrees of freedom, because you haven't measured the electrons. And then you take this electron wave function and you compute the bipartition entanglement entropy of that electron wave function with fixed nuclear coordinates that you've measured everywhere. And then you can repeat 1 to 3, you can average, and what you get out is what I'll call the post-measurement entanglement entropy. It's the entanglement entropy that the electrons have just after you've measured the positions of all the nuclei. Boom. Right. And so what is of interest here is the size scaling of this post-measurement entanglement entropy. Okay, maybe let's say we could have a volume law. So if one did, and that's I think a reasonable guess, is that what that would mean is that the electrons, even after you've measured the frozen position of the nuclei, the electrons are entangled or thermalized even after measuring the nuclear position. So this is, I think, would give one some definition of what thermalization of the ionized electrons would mean. So presumably, a strongly ionized plasma will have a volume law, a post-measurement entanglement entropy. Imagine, though, you have an eigenstate which has an area law. That is, you start with a volume law eigenstate, and you measure the positions of all the nuclei, and that is enough to disentangle the electron coordinates so that the electron wave function that you get after the measurement has an area law. That is, you've managed to induce, essentially full locality in the degrees of freedom, in this case the electron degrees of freedom, that you haven't measured. And if that is possible, if one has an eigenstate like that, we'd call that a quantum disentangled eigenstate. Now, in an atomic fluid with absolutely no ionization, if you just freeze each electron on each nucleus, then it's sort of trivially in this quantum disentangled eigenstate, but then it's kind of a cheat as well, because you have to, you can't really freeze an electron on the nuclei, and there'd be some quantum fluctuations, and so you have to then ask, well, what about in a weakly ionized atomic fluid? Could that possibly have the electrons have an area law entanglement after you measure the positions of the nuclei? So again, for the quantum disentangled state for this atomic fluid, I'll say the atomic fluid eigenstate is quantum disentangled if, when you measure the positions of the nuclei, that disentangles the entropy of the wave functions of the, in this case, light electrons, giving you an area law for this entanglement entropy. On the other hand, it seems pretty clear that even if you had such a quantum disentangled eigenstate, if you measured the light positions of the electrons, that wouldn't disentangle the wave function of the nuclei post-electron measurement. That is, if this state exists, the light degree of freedom, in this case the electrons, are going to be enslaved to the heavy degrees of freedom, not the other way around. Anyway, this is a definition, one definition of a quantum disentangled state. A more general definition is you take a volume law entangled eigenstate, you perform some local partial measurement, and then you look at the wave function of the unmeasured degrees of freedom, and you compute the entanglement entropy of the post-measurement wave function of those unmeasured degrees of freedom. And if the post-measurement entanglement entropy of those unmeasured degrees of freedom is an area law, then you've in some sense induced full locality by making the measurement partial measurement, and I'll call that a quantum disentangled eigenstate. A conventional thermal state would not have that property, presumably. But do quantum disentangled states exist? I mean, is this entirely fiction? I'm defining things, fairly precisely. But when exists, what does that mean? I mean exist as eigenstates of sort of generic Hamiltonians. So let's focus just in the last 5 minutes on fermionic Hubbard models, favorite model for condensed matter physicists. And what is the partial measurement we're going to make? Let's measure the charge on each site, but not the spin. So we'll take a volume law wave function, some fermionic lattice model, and we measure it, and we get the information that on this site, there's charge 2, this site there's charge 0, and this site there's charge 1. Well, if it's charge 1, we don't know what the spin is. So we then have a spin wave function that we are left with, and we can then take that spin wave function and look at the bipartition entanglement entropy of that spin wave function. So the question is, by measuring the charge degrees of freedom, can you disentangle the spin degrees of freedom or not? So we've done and this is really work in progress. I'll see Jim Garrison, a student here, looking at numerics on a one-dimensional Hubbard chain. The details aren't so important. The important thing, the only detail that's important is it's a non-integrable chain. We want to add a Heisenberg exchange interaction to that, and he's using exact diagonalization. So here's some data. This is on a 8-site Hubbard chain with 4 up and 4 down fermions, pathetically small systems, and this is what makes quantum dynamics at finite energy density so damn hard. Classical computers are pathetic for this. If we work in imaginary time and we look at ground states, which have area law and are almost disentangled, things are simple. But if we're really interested in quantum dynamics, such at finite temperatures, it's brutal, numerically, with a classical computer. So, tiny little site. What's plotted here is the full entanglement entropy for all the states, and you see this, this inverted U as before. And now what's plotted on the right hand is the post-measurement, after measuring the charge, entropy of the spin wave function. Okay, it's smaller in amplitude, if you could see the vertical axis. But what's interesting about it is that there seems to be what I'll call some spin disentangled band. It's a set of states which are kind of pulled off from all of the other states. And we can count how many states are in this band, and there's 70, which is 8 choose 4, which is precisely the number of states that you'd have if you had 4 Cooper pairs, because then you could put those 4 Cooper pairs in any of the 8 sites. So it's kind of some sort of paired state where there aren't many free electrons with their spins fluctuating, so it has low spin entanglement after measuring the charge. Now, remarkably, this end state right there is a state that C.N. Yang wrote down, I don't know how many years ago it was there, 25 years ago. He called it the eta paired state. It's a state where you take a Cooper pair condensate at momentum pi, and it's an exact finite energy density eigenstate with 0 entanglement. So we're so used to thinking, at least ground states have area law entanglement or low entanglement. But wait a second, what if you have a state up in the Manybody band, somewhere at finite energy density, which has very low entanglement? Well, C.N. Yang tried to look at states nearby that, but what he didn't find, because he was only looking for exactly soluble states, was this band of states that we're seeing coming off C.N. Yang's state. And so this is what's interesting, is that we believe there's an extensive number of eigenstates in this band, much fewer than the total number, but still extensive. And one could just focus on that band. Here we just made those points look blue. And, okay, that's the A-paired state. Now, over here, if you look with the mother's eyes, you'll see this sort of red inverted U. That's coming from all these states. And then there's an inverted U with blue. That's the A-paired state. That's the ground state. Okay, and so what we want to do is actually look at the entanglement of some of these states after making a charge measurement. So we're going to focus on 3 states: the ground state, a highly entangled state, and a state from this blue band which has the highest entanglement. So it's like a high temperature state in this blue band, right? And let's just look at what the entropy that Jim computes, the entanglement entropy after measuring the charge of the spin wave function. And so here it is. So okay, so the left column is the full entropy, and this is entropy versus x. X is the size of this region A, and it runs from 0 to 8. It goes up and down. So look at the top row. Sorry, this is the ground state. The fact that the entropy is so flat here, that's an area law. This is the very highly entangled finite energy eigenstate. It has this structure, with the slope discontinuity, essentially. That's volume law. And if you look at this eigenstate from this blue band, that also appears to have a volume law. Okay, we obviously have to try to do more finite size scaling, but that looks like it has perhaps a slope discontinuity. Of course, it's a very small system, so we don't have much resolution. But what happens now? That's the full entropy of those 3 eigenstates. When we measure the charge and look at the spin wave function post-measurement, well, when we take the ground state, which is an area law before we made the charge measurement, it's still going to have an area law afterwards. Right? If it's already local, we're not going to, and then we're measuring something everywhere, we're not going to, we might induce a little more locality, but it's not going to become non-local by making a local measurement. And indeed, that's a nice area law. The high entanglement eigenstate, which was a volume law, well, after we make the measurement, I don't know. My guess is that we really, basically should be a volume law. But is this a slope discontinuity or not? It's obviously flatter than here. So we could put a question mark there, but I think this should be a volume law. But what about the eigenstate from this blue band? This is this eigenstate right here, the highest entangled state in this blue band. And when we take the full entanglement entropy and we make the measurement of the charge, then we get something which is pretty flat for this entanglement entropy of the spin wave function. So, okay, is this an area law? Well, we've got very small system sizes, and we're going to try to do scaling as best we can. We can go a little bit bigger than this. But this, I think, at least offers some preliminary suggestion that one might have a band of quantum disentangled eigenstates in this Hubbard model. Now, it's a Hubbard model with an attractive view. And so, anyway, that's the main message. Well, the main message really is that thermal eigenstates may not be just completely random. I mean, I'm sure some of them are essentially completely random, but some of them might have some hidden structure and some hidden locality. But you have to look very carefully to find it. And maybe, okay, one diagnostic we've suggested is that you make a measurement everywhere, but it's a partial measurement. And then you ask, if you make a partial measurement, do you induce a locality on the degrees of freedom you didn't measure? If you make a full measurement locally, you'll get a direct product state spatially. So then it's become fully local. Anyway, so this is a new diagnostic which may or may not be useful in certain contexts, but we're having fun playing around with it. So it's this partial local measurement followed by a post-measurement entanglement entropy of the unmeasured degrees of freedom. And the interesting situation, which we've not convinced ourselves that it exists, but there seems to be some hints for it, is when you have a volume law state, and you could have a volume law state where you have very little local information, and then you do this partial measurement everywhere, and the degrees of freedom you didn't measure are localized as well. Okay, if that is the case, we'd call that a quantum disentangled state. I think, I'm going to be thinking about this for a little while, I hope. We really want to try to identify Hamiltonians which might exhibit quantum disentangled eigenstates. We're looking at these one-dimensional Hubbard-type model. I mean, we're really restricted to one-dimensional models with exact ionization, unless some of us can develop other theoretical tools to try to look at questions like this. And but it occurs to me that if you take what in field theory, what's called finite temperature quantum field theory, and let's go in the canonical ensemble. So we're really looking at the eigenstates, finite energy density eigenstates of a quantum field theory. And let's look at a quantum field theory where there are both very heavy and very light quantum fields. So very heavy fields would be semi-classical. And for someone who's looking at a real distance, I would have thought gravity would be a pretty heavy field. But I mean, and maybe the electrons is a kind of a light field. But in any case, independent of the relevance to any particular quantum field theory, I think if you have a quantum field theory where you have very heavy and very light fields, it's conceivable that you have finite energy density eigenstates where if you measure the heavy degrees of freedom, that is, you make in the case of gravity, you make the quantum fluctuating gravity, you just measure it, and there it's a classical background. Then you ask, does that disentangle, maybe the light particles that were fluctuating around on that background, quantum metric? I don't know. But I think really something that is important, I think, for myself to come to terms with is that entanglement entropy is not the be-all, end-all necessarily. It's one way to try to measure some local, non-local features of a many-body wave function. And there can be other diagnostics. Rob Meyer was speaking to some of these, and I think there can be many, many more. And obviously some of the diagnostics you can make them up willy-nilly, and some of them are not going to be helpful at all, and some might be. The question is, are they, do they describe real physical situations or not? So anyway, that's about all I had to say, and I wanted to just close and say again, happy birthday to Joe, and I'd love to hear some feedback on this work, possibly. I mean, constructive criticism is just fine. Please play defense if you so choose, because I'm an offensive player. So anyway, well, happy birthday, and thanks for your attention.
We have time for questions. Joe first, since.
A short question. If you violate ETH, does that mean you're violating thermodynamics as well? Do some thermodynamic relations fail?
Well, thermodynamics fails.
Yeah.
Because it doesn't thermalize. It doesn't.
That's the point.
It doesn't even.
Now,
in these, okay, so that's with the many-body localized phase. It just,
right.
You heat it and the heat stays there. You put a thermal bath and the heat doesn't get in. So thermodynamics is not operative. In this, if in these quantum disentangled eigenstates, it depends what you measure and what you look at in that wave function. If you just look at the atoms moving around and don't worry about measuring the nuclei and where the electrons are once you measure the nuclei, then it would look like probably thermodynamics and ETH would be valid.
But it seemed like you had two kinds of states. Should I think of that as two phases?
Yeah. Well, okay. So that's what we means by phase is gets confusing, and this is a point I should have emphasized actually. Okay, so that the energy per unit volume, and the energy of this blue band overlaps with the red band. And there's many more states in the red band, right? So you might say, okay, well, if in any physical system, you're more likely to prepare it here than there. And maybe that's true, although, maybe if you start in this eta paired state and then, perturb it weakly, you can actually kind of live in this low entanglement, unionized band. But then this becomes a dynamical question, is how you do the physics. But I would say that the breakdown of the ETH in some sense here is that the wave functions at the same energy, the blue and these red ones, have very different character. Now, while we think there's an exponentially large number of these blue eigenstates, there's an even exponentially larger number of red eigenstates. They're both exponential of the system size. So what would have been most interesting would be to find a region of energy density which is all blue, where every state at that energy has this quantum disentangled character. But maybe that's that maybe you should expect something more complicated like this if you're going to have some sort of breakdown of ETH, even if it's in a more subtle way, involving somehow the interplay between 2 degrees of freedom that you are not measuring. So,
So sorry, I wanted to understand what the upshot was in the ionization example that you started with. I thought I got the intuition that the heavy nuclei were behaving like the random potential for the lighter degrees of freedom. Was that the conclusion, or were you saying it was too difficult to analyze that, so then you went to this special case?
I mean...
Like if you took the nuclei to be high Z or something, can you get a limit where you can solve it or show that this is true?
Well, we can't show analytically that this is true, that, the quantum disentangled eigenstates exist. There's a limit with the heavy light nuclei electrons. If the nuclei are infinitely heavy and they don't move at all, then you can treat them as quench disorder, static disorder. And then the electrons, the light degrees of freedom, move in this random potential, and they can presumably, and this is based on numerics, be in a many-body localized phase. Okay, so then they would have, the electron wave function would be an area law. So why did we not try to numerically look at heavy and light particles? Well, we started looking at that, but you're living with such small systems, and you want to find models where you can try to get information in very small systems. And what we then were looking at here in the Hubbard model was we were doing something in this data, which is measuring the charge, which gives you a lot of information, because you know whether there's 2 electrons, 1 electron, or no electron at every site. So you've almost got full information, so we're not leaving that much information out there, which is what the spins are doing. And so that's kind of, maybe there's a chance that we can have induced locality in those spin degrees of freedom by making this measurement. I mean, there's another diagnostic you can do. You could measure whether or not you have 2 electrons on each site or not. Okay, so you have 2 electrons on this site, you'd find 2 electrons on that site, and then you have no other information. You just have electron wave function moving around. And we've looked at that diagnostic, and it doesn't look as aerial law-like. But so it's possible that with that diagnostic, it's volume law, that if you measure the charge, you can localize the spin, but if you measure whether or not there's a Cooper pair on each site, that the electrons which were unmeasured, the single electrons which are unmeasured, are still in a volume law. Right? So there's sort of many different NIF definitions that you can and try to look at different ones. And the place where you might have the best hope is if you have almost measured everything. Your partial measurement is almost a full measurement, and you just have a little bit left, and maybe that little bit left hasn't been able to thermalize on its own. Right? That's kind of the intuition. Yes.
I'm also thinking of charge spin separation as ionization.
Well, okay, so what you mean the connection between the ionization? I mean, yeah, so this, there are some, yeah, so, in some sense, this blue band, not even in some sense, this blue band, the state here right at the end, this eta paired state, is a state which has no single electron, so it has no spin degrees of freedom at all, right? And so the states near here are just kind of weakly ionized Cooper pairs, right? So you can imagine the sort of virtual fluctuation where a Cooper pair, separates into 2 electrons, which are in a singlet, then come back again. Another one separates into a singlet. And the question is, those electrons, when they have separated into a singlet, can their spins entangle with the other electrons, which are fluctuating out of the Cooper pairs far away? Now, I'm using the language of sort of perturbation theory, virtual fluctuations and so forth. But here we're just looking at eigenstates. So we don't, but I think that picture is probably helpful. So there's some, similarity in the physics with the, with the ionization.
So I'm trying to build some intuition for your diagnostic in continuum field theories. So would you say that if I took a continuum field theory and sort of subtracted off the divergent pieces, then in the disentangled phase you would see sub-extensive growth, whereas in the regular thermalized phase you'd see extensive growth of?
Well, this is a bee in my bonnet. I need John Carty was here the other day, and he said, if you can't put the model on a computer, you don't have a theory of anything. And these continuum field theories, And let me tell you, Joe and I have discussed this. And in fact, when I first came to the KITP, I remember Joe pointing out to me that Steven Weinberg, he was like, can you believe this, Matthew? Steven Weinberg thinks the only way to define a field theory is perturbatively. Now, for a Gaussian theory, the cutoff doesn't matter, and then you can do perturbation theory. But Wilson and others told us, you really want to regularize and have a defined theory, and that, that I think was, what you were conveying to me, and that made a lot of sense. But with the firewall, I pushed you a little bit on, what's ultraviolet regularization, and yeah, my gut feeling is it matters. I mean, that's the physics, which is on the Planck scale, and so you have to, I think, more attention has to be paid to the ultraviolet. I mean, it's. Well, I've got one supporter. Thank you.
Matthew, I frankly find this pretty surprising. Do you think it might be a one-dimensional phenomenon?
No.
You sure?
Yeah, positive. Well, okay. I mean, if it exists, I think it can exist in high dimensions. This eta paired state is an exact eigenstate for a d-dimensional hypercubic lattice Hubbard model. And see, where one's intuition is breaking down, so this eta paired state has, and there's an attractive U, I should have said that. So it looks like it's low energy, and it looks like if you raise the energy, you would start ionizing these Cooper pairs. But actually, you get the ionization when you lower the energy. And the reason this band is sloping down this way is because the pairs are condensing at momentum pi.
Are there propagating?
And just say the pairs are condensing at momentum pi, and so there's a very intricate sign structure. So this Cien Yang's pair state is annihilated by the electron kinetic energy operator.
Are there propagating modes in this state of any kind?
I'm not sure what that means, really. I mean, I think the way I would think about states living in here is that
right at that point, right at that Yang point.
Right at that point, it's just it's an eigenstate. It's just.
I know, but if you disturb it, are there propagating modes?
Well, I mean, I think these states down here, very close to it, can be thought of as states where I mean, different, the way you can disturb it, and with the way waves, I mean, you can.
So, and do they have omega equals k squared?
Actually, they will.
They will.
They will, and that's why it's soluble. Yeah. But I don't think. I mean, yes, that's. But I don't think that's essential. I mean, it's essential to have
so they're like Heisenberg ferromagnet.
It is. I mean, in a way, in some representation, if you go to charge spin duality, this looks like a ferromagnet.
Right.
Okay, I'm going to cut the discussion now. Yeah. Sorry. Let's thank Matthew again. And I'm sure Matthew will answer questions afterwards.